to the things we learned the day before. Well, what did we learn the day before? The day before we learned, in terms of formulas, that centripetal, C stands for centripetal. So when we talk about V sub C, we're talking about circular motion, and we can find the speed of that object by using 2 pi r over t. We learned that t is the period, f is the frequency. It's very useful to note that the period is the number of seconds per revolution, but the frequency is the number of revolutions per second. The relationship between these is that the period is the reciprocal of the frequency, and I'm not going to write it down, but what that also means is that the frequency is the reciprocal of the period. That's what we learned class before yesterday's. All we added on to that was the idea that centripetal acceleration can be found using v squared over r, or centripetal acceleration can be found by taking 4 pi squared r over t squared. And these two formulas on your formula sheet are given in the same line. They're just a string of an equation. AC equals v squared over r equals 4 pi squared r over t squared. I don't feel the need to put vectors and absolute value signs among these quantities. They are magnitudes only. That's the important part. And then there's one other thing. We didn't really learn it yesterday. We learned it the day before, but we applied it yesterday. The thing we learned the day before is that Fc, that resulting force that causes an object to move in a circle, is F net. That net force might be a force due to gravity, it might be a force of friction, it might be an electric force, it could be an applied force, it could be some combination of forces. But in the end, after all of the forces are contributing to the motion, the result is it moves in a circle. So the result is the net force. And since the result is circular motion, the net force is now called a centripetal force. What does that mean? It means that you can write F net equals ma, and you can say that's centripetal acceleration, and you can say that it's centripetal force. And I'm really hesitant in not leaving it as F net. I don't want you to think, you know when we did forces of friction, and in the formula for force of friction, which was this, if the object was on a horizontal surface, we did this, right? So what we're saying here is that the normal force, we're saying this. I don't want to say it in words because I would be wrong. That's true, right? But are these the same force? No, they're not. They're different forces. One is down, one is up. What we're saying is the magnitudes of these forces happen to be the same, but it's different forces. Over here, when I say that F net becomes Fc, I'm doing that because F net is Fc. That's what the force is. So I don't want you to think that these are two different forces. I don't even want you to think, well, the centripetal force is the only force, so it's the net force. Don't think that way. The net force is the centripetal force. And what this means, looking at these three formulas on the left-hand side of the screen, is if you ever are asked for the net force or ever are asked for the centripetal force for circular motion, take the mass times the centripetal acceleration. There's no formula for Fc on your formula sheet. You have to build it. All that being said, does anybody have any questions from any of the assigned problems? Go ahead, Aoki. Number 2? Okay, let's take a look at number 2. A small plane makes a complete circle with a radius of 3,282 meters in 2 minutes. What is the acceleration of the plane? We have two options here, Aoki and everybody. We could say that I'm going to kind of flip back and forth. I'm going to put the absolute value signs with the vector symbol. And when we read this question, by the way, it probably should say what is the magnitude of the centripetal acceleration. Okay. But this is equal to v squared over r, so we can use this formula to calculate the acceleration if we want, or in this case, we can use this formula. And, you know, from strictly a problem-solving standpoint and an economy standpoint, trying to get to the answer as quickly and efficiently as possible, the second formula is better. I just don't prefer it. As a teacher, and I'll tell you why I don't prefer it as a teacher. I thought a little bit about this. It's confusing. You look at this formula and you wonder, where is it even coming from? Whereas the formula on the left is circumference over time. That's speed. The formula that you use to find the speed here is circumference over time. I thought I wrote it down, but I didn't. So, bottom line, Aoki, we have two options. We can choose to calculate the speed first and then find the acceleration, or we can just do it in one shot. Which would you like? And don't pick one because you think it's what I would do. What would you like to do? The one-shot deal, the one on the right. Sure, it makes sense. So we do know the radius is 3,282 meters. We know that. We can put that number in for r. And we do know the period. It says it makes that revolution, that complete circle, in 2 minutes. But we do have to remember to put the time in seconds. So now we're just going to take 4 times pi squared times the radius divided by t squared. And again, we are in learning and teaching mode right now. I don't care about the units. I mean, we have to use the right units, but I don't care about writing them down. Over 120 squared. Four pi squared times the 3282 divided by 120 squared gives me 8.99 or 9 meters per second squared. There's another issue I have with this formula, and maybe it's my personal problem, but students are like this too. Very often they forget to square the time, and sometimes they square r instead. I don't know why. It seems like r should be squared for some reason, but it's not. Anyway, is that okay? Other questions? Go ahead. Okay. Let's look at number 4. So you have an electron, a little tiny, tiny, itty-bitty electron with a mass of 9.11 times 10 to the negative 31 kilograms. It's moving in a circle of radius 2.00 times 10 to the negative 2 meters. The force acting on the electron is given. How fast is the electron moving? So what I would like us to try to start doing is building an equation. In this unit, sometimes it's okay to use one formula to calculate something, then use that answer in a different formula to calculate something, on and on and on. Remember the projectile motion problems? We did a lot of that. You found the time, then you found the acceleration, then et cetera, et cetera. So, but here I would like us not to do that. We're talking about a force that causes the electron to move in a circle. So there's some net force acting on it. And that net force causes centripetal motion. And you know what, everybody? I'm not even going to call this net force centripetal force. It's the net force. But since that acceleration is centripetal, we're going to replace that A with what centripetal acceleration is equal to. So, centripetal acceleration is equal to either v squared over r or this beast, right? So we have an option. Now we're going to have to read the question carefully, because if I put in this for the acceleration, if I write the following, and I'm going to put it in a different color and erase it in just a minute, I can't answer the question, because although I'm told the radius, I'm not told how long it takes to go around, and there's no way to find that. But I am told the speed, aren't I? Am I not? Oh no, I'm trying to find the speed. Wow, that's all the more reason to put this in instead, because we need to find the speed. So we can put v squared over r. So F net in this case, because it's circular motion, is mv squared over r. I will tell you right now, anytime it's circular motion, the net force is mv squared over r. Or m times 4 pi squared r over t squared. So now what we can do is put in the numbers. We have the force, which is 4.6 times 10 to the negative 14, equals the mass, which you're told is 9.11 times 10 to the negative 31 kilograms. And again, I'm leaving out the units because mathematically it's easier to look at how we rearrange the equation if we're not trying to see through all of those units. Units are important. We need to make sure we're using standard units of newtons for the force and kilograms for the mass. This is times v squared over r, and r is 0.02 meters. You could certainly write down 2.00 times 10 to the negative 2, but that's what it is. Okay. So how do we rearrange this? Well, if I cross multiply 0.02 times this number will be equal to this number times v squared. So all I'm doing is cross multiplying. I'm taking the bottom of one side times the top of the other and setting those two results equal to each other. And I can do that because it's just a fraction equal to a fraction. So that means that to get v squared by itself, I can multiply these two numbers on the left and divide by that mass of the electron. And that's going to be v squared. .02 multiplied by the force of 4.6 times 10 to the negative 14. That is the force. Can you just double check? 4.6 times 10 to the negative 14. It is good. And I need to divide by the mass of the electron, 9.11 times 10 to the negative 31, I was told. So just double check. I'm multiplying those two numbers and dividing by the mass, and I hit equals, but I need to take the square root. Okay, this is just v squared. So if I take the square root of that answer, I get 3.2 I get 3.2 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters per second, or maybe 3.18. I don't know, probably 3.18. Yeah, I should have an extra decimal there because everything had 3 digits. Anyway, is that okay? All right. Other questions? All right, so now what we're going to be doing in the next few days of classes, we're going to have a lab somewhere in here, but tomorrow our class is cut short due to the Remembrance Day ceremony, and I'm not quite sure how much time we're going to have left. So you will be called down to the gym sometime tomorrow during your period 2 class, the class before this, and the Remembrance Day ceremony will probably go until 11:15. Which means, and I know how that goes, which means it'll end at 11:15. By the time everybody gets back to classes, we're probably not going to start till 11:30, maybe. maybe a little earlier. We're not going to have a whole lot of time tomorrow. So I was planning on doing a lab tomorrow, but I don't think we're going to have enough time to fit it in. We might just do a lot of extra practice tomorrow, or you might have an assignment that's given tomorrow, or I might give you a quiz tomorrow. How about that? I don't see a lot of enthusiasm for that idea. Luckily for me, you don't make that decision. I do. I think we might have a quiz tomorrow. Maybe. Or I could just be telling you we're going to have a quiz so that you do your work. And I could just be telling you that because we really are having a quiz. Yeah, reverse psychology. Exactly. So, 20.3.3. In the next few days, what we're going to be doing is applying circular motion. And this, on your handout on page 11, is page 11 correct? Should say part 3. Mine says part 2, but it is part 3. So we're looking at two very specific applications today of circular motion, or applications of centripetal force. One is artificial gravity, and the other is when the centripetal force is produced by friction. To begin with, we'll start with artificial gravity. There's this thing called the human centrifuge, and the idea behind a centrifuge is if you have a test tube, and the test tube contains, so this is a test tube, and it contains some mixture of materials. There's liquid and there's little particulates. How many of you are in chemistry 20 right now? You talk about precipitates yet? Yeah. Okay, so when you mix two solutions, you might get a precipitate forming, which is a solid forming, and how you would separate them in class is you would dump that all onto a piece of filter paper and let all of the liquid go through. You'd probably rinse all of the precipitate with distilled water, and then you would dry it overnight, and then you have your precipitate. But sometimes a very quick way to separate them is to put this test tube in a centrifuge, which is going to take this test tube with this mixture of stuff, and it is going to spin it around a common point. So it doesn't lay flat. It's kind of at an angle. It's like this. But the common point is here in the center. And when this thing spins, the particulates, the precipitate, end up getting kind of pushed to the bottom. Now, they don't get pushed to the bottom really. What happens is the lumps of material in here at this point in time are moving this way, aren't they? So they move that way, but the test tube moves out of the way. So they continue to move in a straight line, but the test tube ends up being here. And that means that these particles that move in a straight line find their way closer to the bottom of the test tube. There's no outward force. This is one of the things we're going to have to grapple with in this unit. What a human centrifuge is putting a person in that position. And usually, at least when we're talking about test pilots and pilots learning how to withstand high G-forces, they're sitting in a chair. So you can imagine that what's going on here is I'm in this human centrifuge, and I'm spinning this way. But it's not a vertical thing. In reality, and I don't feel like getting down on the floor, in reality, I'm sitting in a chair that's like this, and this thing is spinning around. It's actually spinning this way. So when I'm sitting in that chair, if it's spinning that way, I feel this force pushing me to your left. So that's a way to produce artificial gravity. There's another catch to that we'll talk about in a minute. But basically, the centripetal force exerted on the person towards the center is felt on their bum, right? And that means that you feel forced in the opposite direction. We've talked about this with gravity. When I stand on a scale, the reason why the scale reads a force is it's measuring the force that it pushes up on you with. You feel, though, pushed in the opposite direction. And how many of you have heard of centrifugal forces? It's an imaginary force. It means center fleeing. So when you're in a car and you're traveling very fast and the driver turns left, you feel force to the right, don't you? But you're not. It's just the car is forced in the opposite direction, so you feel force to the right. We don't want to talk about centrifugal forces, but I've got it here because sooner or later somebody says, well, what's a centrifugal force? It's an imaginary force. It's what we perceive. So the person is usually seated so their head is towards the center of the rotation. Human centrifuges are used to train astronauts. Astronauts, pilots. So here is somebody in one of those right now. There's a close-up of their face, and there they are seated. The G-forces right now are 1.57. So if you take your calculator and go 1.57 times 9.81, that's the rate of centripetal acceleration. About 15 meters per second squared. Okay. You can keep track on this. It's a little blurry, but we don't need it to be enlarged. I think you can see it quite well here. I'll go the medium one. You can keep track of the G-forces that this person is subject to. It's only about a minute and a half. I would say their heavy breathing right now is probably more a result of them being nervous than being under the physical stress of a high G-force. So now they're up to 9 Gs. Like, think about, I just want to pause for a second. Look at his face, right? The skin on his face is being drawn down to the bottom of his head. And just think about this. I don't know what the human head weighs. 5 pounds, maybe? I know there's a movie with a classic line of, oh, did you know the human head weighs 5 pounds? I don't know if that's true or not. But 5 pounds is about 2 kilograms. It's pretty, it's not heavy, but you wouldn't want to carry it around all day. At 9 Gs, that's like having not 5 pounds supported by your neck, but 45 pounds. That 45 pounds is one of those big water jugs. And if you've ever had to carry one of those big water jugs from one place to another, you know it's heavy. So imagine that I sit you in a chair and I put one of those on your head. That's the stress that's on this person's neck right now. And that's why he looks like he's working hard to keep his neck vertical. He probably has a kill switch that could immediately slow down the rate of rotation very quickly. So now he's going back down to about 3 Gs. The rapid breathing now is probably as well due to mental stress, but also physical stress. Because just like swinging that ketchup bottle around brings the ketchup to the outside of the circle, his blood is going to the outside. And the heart is working hard to pump that blood up to his brain, and it becomes very difficult. Most people without training would probably black out at about 5 or 6 G. And I guarantee you, I don't know for sure, but I don't think this is the first time this guy's done it. I don't think they strap you in and go, okay, let's hit 9 Gs and see what happens. You have a few days of training at 3, 4 Gs to get used to it. There's another one. This guy is just so calm. It says more 30 seconds at 9 Gs. The G monster is back. This guy, if you watch him, he is just so laid back. He's done this a million times. He's answering questions. It's a long thing. I don't want to play the whole thing, but he's just kind of, we'll get to the part where we'll start there. So he's at 2.7 Gs, and he's kind of, okay. You can see his face starting to drop a little bit. 4 Gs. Okay. I think they probably asked him, are you okay? Yep. You'll notice, though, they're jacking them up more slowly, right? That other guy went from 3 to 9 Gs in about 3 seconds. So again, his head is like one of those water jugs right now. So feel free to check out human centrifuges on YouTube, and you can watch these yourself. Okay, let's get back to the lesson now. I've already mentioned this, but if you start to get up to 7 or 8 Gs, you can lose vision. I don't know the exact biology of that. Not permanent, I don't think. But I think the blood is being drained out of your eyes, and your eyes are not functioning right. So how many of you have ever blacked out? Like I have. When I was very young, I got out of the shower, and for some reason, everything went. That's what I remember. Is it just started getting blacker and blacker and blacker, and then boop, nothing. And then you wake up. That's what happens when you have vision loss, is you have all of this stuff you can see, and it starts getting narrower and narrower and narrower, and then you can't see anything, and you black out. Higher G-forces can result in permanent damage, which I think would be obvious. If the radius of a centrifuge is 4.5 meters, what is the speed and frequency if you're going to experience 1 G? Well, all this means, everybody, is that the centripetal acceleration has to be equal to 1 G. That's all that means. Here, the centripetal acceleration has to be equal to 3 Gs. That's all it means. Now, I haven't answered the question. I don't mean to just hand wave it away as if we're done. We're not. But what this means is v squared over r has to equal 9.81. Here, v squared over r would have to equal 3 times 9.81. But, rather than, no, I won't do that yet. Let's calculate v for 1 G. How fast is the edge of this centrifuge moving? Was it 4.5 meters, the radius? So I would have to take 9.81 times 4.5, and then I have to take the square root because I'm trying to find v. So I get 6.6 meters per second. If I wanted to find the period and frequency, well, the speed is 2 pi r over t, so the period would be 2 pi r over the speed. Cross multiply and divide by v. So I would take 2 times pi times the 4.5, and I would divide by that 6.6 meters per second. It's 4.3 seconds. Now, 4.3 seconds is a long time, right? I mean, it's not. If I said I'm going to throw something at you and you have to be ready in 4.3 seconds, you could be ready, right? But try to imagine from the center of the room, I would say 4.5 meters is probably to the opposite side of that first counter. So that object that's over there is going 1, 1,000, 2, 1,000, 3, 1,000, 4. Like you're moving along at a pretty big clip, right? 6.6 meters per second. What's 6.6 times 3.6? What's 6.6 times 3.6? 23.76, so 24 kilometers per hour. You can't run that fast. Well, I can't. Olympic runners can. They can reach peak speeds beyond that. I don't want to get too far off topic, so let's just finish this off. The period is 4.3 seconds. The frequency, frequency is 1 over the period, right? That's how we do it. So you go 1 divided by 0.43, or 1 divided by the period. The frequency is about 0.23 hertz. So there are our three answers. Look, I'm not going to write down all of this stuff for each of them. I'm going to do it on my calculator. You can follow along. Make sure you know how to do this. At 3 Gs, all we're going to do is take 3 times 9.81 times the 4.5 meters. That's v squared. I need to take the square root of that. So about 12 meters per second. And I'm not going to be going slow enough for you to write down all of this work, because we have like 5 or 6 calculations to do here. Looking at how we found the period before, period is 2 pi r over v. So if I take 2 times pi times the radius divided by my speed, this is the period. All of a sudden, it's only taking about 2.5 seconds to go around once. And frequency is 1 divided by the period. So our answers for the 3G one would be this is the speed, this is the period, and this is the frequency. Do we have 2 more? Okay. 5G, well, I think you can see things are going to get out of control very quickly here. Like, not out of control, but you're going to be moving very, very fast. So this time we have, I'll write this down so we can see it, v squared over r equals 5 times 9.81. Here we're going to have v squared over r equals 10 times 9.81. Let's just for these two, well, let's find them all, I guess. Won't take long. 4.5 meters times 5 times 9.81, and then take the square root. So at 5G, you're moving at 15 meters per second. Moving along pretty fast. 2 times pi times the 4.5 divided by the speed gives us the period. So the period is only 1.9 seconds now. And then the frequency is 1 over the period. So now what we're talking about is this speed, this period, and this frequency. And then at 10 Gs, this is a wild ride, times 10 times 9.81. Take the square root. We're getting about 21 meters per second. You're getting, it's not quite 100 kilometers per hour, but it's, in the 80s probably, times 3.6, close to 80. 2 pi times the radius divided by that gives me the period. That can't be right. Yeah, it is. Is that right? Yeah. Okay. Right. Right, and that's, I guess, the true test is if you're going to a higher g-force, you must be going more rapidly around. The frequency must go up. So 1 divided by that gives me that. So this time we have the speed, the period, and the frequency. We're still good? The bottom line here is you set the centripetal acceleration equal to whatever the simulated acceleration needs to be. A long time ago, there was a movie, long time ago, 1969, 31, 41, 51, 53 years ago, there was a movie called 2001: A Space Odyssey. Have you ever heard of it? Has anybody seen it? It's a hard movie to watch. It's a classic, and every time I go, I'm going to watch it, I lose interest. Like it's very weird. Anyway, based on a short story written by Arthur C. Clarke called The Sentinel. And in it, they have a satellite in orbit, a space station in orbit, that's spinning, and it produces artificial gravity. And this is not science fiction. This is science fact. You can easily make something like this. The diameter of this thing is 75 meters. So that's a diameter, which means the radius is half of that, which I think is 37.5 meters. But I just want to make sure. Good. So remember when I said that if the person were seated and it were spinning this way, they would feel pulled down? Well, imagine it's outside of, I don't want to say outside of Earth's gravitational field because it's in the gravitational field, but it's far enough away that Earth's gravity is not important. Imagine that it's spinning vertically like this, and I'm being pushed down against my chair, and I go, well, why don't I just stand up and I can walk around? And I can walk along this thing all the way around. That's what we're talking about here. So the question is, if you want to simulate gravity that we experience on Earth, at what rate must it rotate so the people inside the ring experience Earth's gravity? So at what rate must it rotate? That is asking me to find t, basically. How many seconds does it take to go around once? Or what's the frequency? And we're going to be, many of you will be surprised by the answer. Okay? It's not going to seem right. So all we're going to do is say that v squared over, well, I guess we're going to have to use this. 4 pi squared r over t squared equals 9.81. We pretty much have to use that formula because we're trying to find the time directly. If it said how fast does the outer edge move, we would use v squared over r. What do I have to do here to find t? If I cross multiply, I get this, right? So I divide both sides by 9.81, and I get t squared equals 4 pi squared r over 9.81. This is the usefulness, I think, and the ease of things if you know how to rearrange an equation first. You don't even need to write down the numbers. There's the answer. This is the answer. We just have to throw that into our calculator with the numbers. This is centripetal acceleration on your formula sheet. If we want the centripetal acceleration to match the acceleration due to gravity, then that's why we're setting them equal to each other. What do we get here? 4 times pi times pi squared times 37.5 divided by 9.81. 4 pi squared times 37.5 over 9.81. Take the square root. 12 seconds. And that, to me, that's initially surprising because you think 12 seconds? That doesn't really seem like it would be moving fast enough. But if you go 2 times pi times the radius divided by that time, you're moving at almost 20 meters per second. It's fast. And by the way, if acceleration is v squared over r, if I square that and divide by 37.5, I better get 9.81. But the answer to the question is 12 seconds. Okay? It's rotating at a rate of 1 revolution every 12 seconds, or 12 seconds for every 1 revolution. All right, let's talk about a second application now, which is friction. This is a hard thing to wrap your head around, and I don't want to spend, I think tomorrow will be a work day with this stuff. I don't want to spend too much time trying to get you to wrap your head around this. But when you have a car, here's the car. This is the top of the car. Here are the tires. Some kind of Tesla monstrosity. And we'll just say that the headlights are here, just so we know where the front of the car is. And the person is driving forward. They're not in reverse. Okay? So they're traveling to the right. If the road is curving, and they want to change direction, so I'm going to have to just adjust something here. If they want to follow that curve, and we talk about the forces acting on the car, if they're traveling at a constant speed, what that means is that there's a forward force of the engine at that point in time, and there's a backwards force of friction. But if they're traveling at a constant speed, they're not speeding up or slowing down. Those forces are equal. Is there a force of gravity acting on the car? Well, yeah, it's not a magic car. But I'm not going to draw the force of gravity. And maybe what I'll do is I'll just put this for V. That's the direction it's moving. I'm not going to draw the force of gravity because the force of gravity would be in our diagram. It's towards the ground. And it's balanced by a normal force. But if those four forces, this one, which is the force that the engine exerts, this one, which is a force of friction, which is balancing that force, and the force of gravity towards the road and the normal force away from the road, if those are the only four forces, then they all balance. And if they all balance, there should be no acceleration, which means the velocity shouldn't change. But the velocity is changing because the direction's changing. That means there has to be some force pulling the object to its right from the driver's perspective. What is that force? You know what that force is? It's a force due to friction between the tires and the road. When you turn the tires in that direction, they produce a force in that direction. The reason is basically that, it's very hard to explain, but the reason is basically that the tire is rolling this way, and there's friction between it and the road. When you turn the wheel in this direction, you're pushing against the direction it wants to rotate, so the force of friction moves it that way. And if you're watching this on a video, you can't see what I just did, but that's why when you turn the wheels, you change directions. And that's why there's a lot more wear and tear on the tread if you're going around curves continually. Whereas when you're going just forward without spinning your tires very much, or you're slowing down without skidding, there's very little wear and tear on the tires. But the bottom line here is, in this situation, this little beast is the net force. Because all of the other forces cancel. Now think about this for a second. Net force is centripetal force. Are you with me? So what I'm saying is, in this case of a car moving around a curve, the net force is equal to the centripetal force, which is equal to the force of friction. Are these three forces? Are these three different forces? They're not. It's the same force. The force of friction is the net force. The net force is the centripetal force. The force of friction is the centripetal force. It's just three different ways to talk about it. The force of friction is the net force because it's the only one that is not balanced. And the force of friction is the centripetal force because it causes centripetal motion. All right. So, assume that the coefficient of friction between the tires of an 1,800 kilogram car on the road is 0.75, and I'm pointing out to you that that's pretty typical. Unless it's icy, like it was yesterday morning, in which case the coefficient of friction might be 0.1 or 0.2, as I found out when I left my driveway and just kind of slid down a little bit. By the way, as soon as that happened, I pulled back into my garage and I loaded my sandbags onto the truck, increasing the force of gravity on the truck, therefore increasing the normal force, therefore increasing the force of friction. Right? Car is driving around a circular curve of radius 60 meters. What's the force of friction between the car and the road? Well, that's got nothing to do with the motion. It's mu Fn, which is mu Fg, which is mu times m times g. Alex, why am I allowed to make this crafty move?
Since it's on a horizontal plane.
Correct. Why else? Like, why?
Since it isn't at an angle, that means it has to be equal and opposite.
That's what I'm getting at, is these two forces, the normal force and the force of friction, are not the same force, but they are equal in magnitude and they are opposite in direction because it's on a flat surface. By the way, when you go around a curve on a highway, most curves are angled a bit, which increases the force of friction and allows you to go faster. If they're not angled, then they just put the speed limit down a bit more so it's safe. So we can calculate this. This is mu 0.75 times 1800 I saw times 9.81. .75 times 1800 multiplied by 9.81 gives me 13,243 newtons. Are you getting the same answer? Yeah? Okay, good. Now, keep something in mind for the next part of this little investigation. That's the force of friction between this vehicle and the road, no matter what it's doing, as long as it's on a level surface. So whether it's going fast or slow, or whether it's going in a straight line or in a curve, that's the force of friction. What's the centripetal force needed, which is the net force, if the car is going to travel at 55 kilometers per hour? Well, the net force, which is the centripetal force, is ma, but the acceleration is a special acceleration. It's centripetal acceleration, which is v squared over r. So if we want to find, and again, notice I didn't actually write Fc, because Fc is F net. If we want to find the centripetal force for all of these, we need to go v squared over r times the mass, because v squared over r is the acceleration times the mass gives you the force. Okay. Again, I don't think it's really necessary for me to write down all of these numbers, but we do need to take the speed in meters per second, in kilometers per hour, and convert to meters per second. And then I need to square that and divide by the radius. I cannot remember the radius.
60 meters.
60? And what this is, everybody, is the centripetal acceleration. I still need to multiply by the mass, so I get that many newtons. Now I'm going to show you something you can do with your calculator. And we still have 25 minutes left. I'm not too concerned about the time anyway. But what we could do is this. So you can follow along with this. I'm going to go to my lists, stat, edit. Have we used our list in this class before? I believe we have. I can't remember why, but we've used them. I have stuff in my lists. I want to clear it. Does anybody remember where I would go to clear my lists? Second plus, into the memory menu. Right? Second plus, clear all lists. So what I am going to do, stat edit, is in list 1, I'm going to put all of my speeds. 55, 60, 65, 70, 75, 80, 85. Those are all of the speeds. Are you with me? What list are they in? L1. Okay, so let's quit out of here. What is it I have to do to the speed to get the force? I have to take 1800 times the speed squared, but I need the speed in meters per second, right? You know what? Let's do this instead. I need the speeds in meters per second. So I'm going to take the speed and divide by 3.6, right? But look how I do it. L1. See there's an L1 there? I'm going to go L1 divided by 3.6, and then I'm going to hit my store key. This is going to go into list 1 and take every entry and divide every entry by 3.6, and I'm going to store it as L2. It shows me the list. I could scroll through this. But if I go stat edit now, as if by magic, I have a new list, L2. These are the speeds in meters per second. If I want to find the forces, well, I can quit out of here and go 1800 m times the speed squared, but the speed is in L2, so times L2 squared, divided by 60. What do you think I'm going to do with that new list I'm going to create? Store it into L3. This is a nice way to do repeated calculations, because then I don't have to keep doing the same thing over and over again. I do it once I've loaded the data into my list. So now if I go stat edit, here are my answers to these questions. At 70 kilometers per hour, it's 8,300 newtons. At 60, it's 8,300. At 70, I guess we weren't doing 65 for some reason, eh? Does yours have a 65? It doesn't. Okay. So at 60, it's 8,333. At 70, it's 11,343. At 80, it's 14,8. At 75, 13,021, etc. Are you with me there on, in principle, how we can calculate these? I just don't want to spend a whole bunch of time rehashing the calculations. Take a minute and write them down. The numbers are what are important, and you don't have to write all the decimals. So why are we doing this? Well, just take a look at your answer to 3A. The force of friction between the car and the road is 13,243 newtons. And that force of friction is the force that causes the circular motion. 13,200. Is that enough to cause the car to safely go around the track at 55? Yes, because the only thing that's required at 55 kilometers per hour is 7,000 newtons. You can go around the curve very easily because the force of friction is more than enough to cause that motion. Is it enough is the force of friction good enough to cause this car moving around this curve at 85 kilometers per hour? Can it do it? It's not enough force. So what does the car do? It just continues in a straight line, which means it hits the ditch. Somewhere in here, we are asked to find the maximum speed. Is this the final example? Good. Well, this requires an awful lot of thought on your part. I know this from experience. If the force of friction is bigger than the net force, which is the centripetal force, you're fine. If the force of friction is smaller than the net force needed, not good. This is safe. Not safe is maybe even an understatement. It's just not possible for you to go around the curve at that speed if the force of friction is smaller than the required net force. So where's the tipping point? Where is that speed that would be the biggest speed possible? It would be if the force of friction equals the net force. I know we know what the force of friction is, but I'm going to start from the beginning and say this is mu Fn equals ma. You have to think carefully here and know how to develop this equation. The normal force for a car on a flat track is the force of gravity, and this acceleration is a special acceleration. It's centripetal. So look at this formula now. Is this on your formula sheet? No. None of this is on your formula sheet. It's coming from here. We can go further because Fg is mg, and A centripetal is v squared over r. This is interesting. Well, I'm interested by weird things sometimes, but I think this is interesting physically speaking. The masses cancel. The maximum safe speed of the vehicle around this curve doesn't depend on the mass, which is why they don't have around a curve 80 kilometers per hour if you're driving a big truck, but if you're driving a car, go 90. It doesn't matter. Which is weird, because you'd think it would matter, but it doesn't. So I can solve this for v now. I multiply both sides by v and get, by r and get this. So v squared equals what looks like rug, but it's r mu g, which means v is equal to the square root of the radius times mu times g. This thing in the center of the screen right now, this whole thing, is important for the other part of today's lesson. Artificial gravity, you set v squared you set v squared over r equal to the number of g's. Cars moving around circular tracks, you start with force of friction equals F net and build it. So what's the maximum safe speed? Let's see, the square root of the radius times 0.75 times 9.81. Take the square root. The maximum, that cannot be right. Oh, I already did take the square root. 21.01 meters per second. This is the maximum safe speed. I'm going to do that again. Square root 60 times 0.75 times 9.81. This is the maximum safe speed. The answer to the third question. If I multiply by 3.6, it's somewhere around 76 kilometers per hour. So if we go back and look at this, at 75, it was 13,021 newtons, and the force of friction was 13,243 newtons. Is the force of friction enough for 75? Yes. If you knew these numbers were 100% accurate, would you drive around this curve at 75? I wouldn't. Because maybe the road conditions suddenly change and the coefficient of friction goes from 0.75 to 0.74, and it might not be safe. So the Department of Highways would probably put a maximum of 65. All right. I want you to get started on these. Let's say that for tomorrow, well, you still have 20 minutes. Let's get started on these. Let's get as much done in class as we can today. Text 267 and 268. Those are problems that deal with artificial gravity. And then there are 4 more questions, I think, 4 in your handout. I believe those deal with cars on circular tracks. So tomorrow we'll get some more practice. We will have a quiz tomorrow, okay, on circular motion. But we will not have it at the beginning of the class. We'll have it near the end of the class after I've had a chance to review everything. Capiche? Okay, get started here. You got about 15, 20 minutes left.